My name is Wenqing Li. I'm a postdoctoral associate from Professor Seifsu. And today I'm going to talk about backdoor attack detection in deep neural networks. I will first introduce what is backdoor attacks, and then I will move on to our defense method based on coherence optimization. And finally, I will present some new experimental results. But first, I will introduce what is backdoor and what backdoor works in deep neural networks. So, backdoor attacks is typically happens at the outsourced training stage. Outsourced training means people remove their training process out to the cloud platform, and due to the computational burden, like the increase of data size and the model size. So in this outsourced training stage, the attacker insert hidden backdoors to the neural networks so that the attacked neural networks will behave normally on the benign input and will perform maliciously when the input is embedded with trigger, and the backdoor will be activated and they will output a malicious result. And currently, data pointing is a straightforward and widely adopted backdoor method. It's like the attacker inserts a trigger to the benign data and to obtain a poison data. So when the trigger show up in the testing stage, the backdoor neural network will be activated and output a malicious result. And the goals of backdoor attackers is threefold. And the first is efficacy, which means the poison data should be misclassified to their specified class. And the second is fidelity, which means the backdoor should not influence benign data, and the benign data should be correctly classified. And the last is the specificity, which means the poison data and the benign data should be perceptual similar, which in other words says the poison data should not be easily detected. So, and in a mathematical form, the attackers aimed to obtain a trigger pattern and the model parameter W by minimizing three items, which correspond to the three goals. The first is fidelity. This item measures the misclassification of benign data. And the second item corresponds to efficacy, which measures the misclassification rate of the poison data. And the last is the measures specificity. And for this, the next one, the dx is an indication function, and it equals to 1 if and only if the x can be detected. And we note that one of the ultimate goal of the attacker is to obtain a trigger pattern. So for the backdoor attack, trigger exploration is very important.
But just a question. So by fidelity, it means that the attacker wants to point out a specific set of the outputs, right?
Sorry, can you repeat again?
By fidelity, it means that the attacker wants to attack just a particular subset of the outputs. Is it correct? Or
for fidelity, it means the attacker.
So that at least the other set of the outputs is correctly classified.
Yes. Yeah, it's not influenced by the attacker.
You understand it's more about the input, right? It's adding more input, right?
Or
The
is
backdoor,
changing it?
I mean, it's you are adding some input which is wrong, right? Which is
It's not, it's
Or modified it?
yeah modified.
modify some inputs.
How does this compare to adversarial?
Adversarial attacks, it first
Looks very
it,
similar.
it's implemented at the testing stage.
No, you can do it adversarial training.
Yeah, but and another difference is that adversarial typing, they do not require to like to have the
Fidelity.
yes, the second goes the fidelity. They do not require this. The benign data should be correctly classified. They just want the point data is misclassified. This is enough for adversarial typing.
Okay, what is the goal of introducing this type of attacks? This backdoor.
Just could you speak out more little louder?
What is the goal? Like for fidelity, for instance,
Fidelity means the
you are introducing some, say, perturbed data, wrong data. And do you want to verify the stability of your neural network or?
no.
Okay, no. So what is the goal? Just to what is the goal? Like just to design an attack that
It
make
is
your
right that if I insert some hidden trigger in the point data, and when the trigger showing up in the testing input, and the attacked neural network will output a malicious result. And when in the testing stage, when there's no trigger shows up in the input, the attacked neural network works normally.
So a concrete example would be a stop sign, right? So your car sees a stop sign and it classifies it as a stop sign every time. And this is the backdoor network. But then say someone comes up and puts a post-it note on this, a very small post-it note in the corner of the stop sign. Then this network would classify it as something else, like a speed limit sign or something.
Yeah.
So you want it to work the way it's supposed to, but on very unexpected, so something that you can't anticipate during training, like a post-it note in the corner of the stop sign, it does something malicious, right? So I guess that's the difference between kind of a backdoor, it's all adversarial attacks, right? But that's kind of what makes these special is that they're kind of sneaky. They work well in most situations, but they're very specific inputs that make them behave very poorly.
Is it correct, like thinking of it as a comparison with a self-correcting algorithm for encrypting data? Like I know there are these algorithms, perhaps better than me, but you want to save your data in a string, in a form of string 0 and 1s, and there are ways. Like you had some information that if the data is the data inside the string has some errors, that the algorithm detects the error and can correct it.
Yeah, error correcting codes,
Yeah.
I think. Yeah, the two things are related.
Okay.
So you can do error correcting codes on just the input. So there is a relationship, except this, what you're attacking really is what the trained network does.
The backdoor attack typically happens at the training stage. And then, so the trigger exploration is very important for backdoor attacks. Okay. So, and typically there's 3 kind of triggers. First is the very preliminary trigger, that is a visible trigger. And this is like you attacker add a stamp on the image, like the traffic sign, add a flower on the stop sign, then the backdoor neural network classified it as a speed limit. And the second is the invisible trigger. So in this case, the trigger is noise with small magnitude. So this it's not that easy to be detected. And recently, there's more advanced trigger design method called hidden trigger. In this case, the point and the image here is the dog, and it looks like the natural target image, which is the category of dog, and the point image has similar features with the patched source, which is a clean source, and adding a stamp or other kind of triggers. So in this case, when you add a stamp on the airplane, the attacked neural network will output dog, and others will output the correct labels. This is the three kind of hidden triggers, and we can see although the point data looks like very similar to the clean data, they just some differences. Based on this, we propose our method. First, I will introduce some preliminaries. We analyze the presentations from each layer of neural networks, and we have some observations. This is the observation is first is the representation of higher or deeper layers for each object approximately lying in a linear subspace, and representations from different objects lying in different subspaces. Some figures show this observation. First is how the data manifold changes from layer to layer. And in this table, we calculate a flattened matrix based on the Euclidean distance and the geodesic distance. And the smaller is the flattened matrix, and it means the representation subspace is more flattened. And we also adopt some typical linear classification method to see whether they are separated. And we can see at the last layer, they're almost separated. So we got this observation 1. And then we analyze the properties of backdoor neural network in a similar way. We first calculate the flattened matrix for both the target and important data sets. And we can see this matrix is also very small, indicating that they are almost flattened at the last layer. And we plot some of the presentations at the last layer from the line and the important data. It shows that they lie in two different subspaces. So our second observation is that the genuine data and the important data approximately lie in two different linear subspaces. So
This is not the data. This is
yes, the representation. Sorry.
neural representation.
Yeah. So based on our two observations, we come up a very simple and effective way to detect backdoor attacks. The insight is that if we, first, I will introduce this figure, and X1 is the benign representation lying in S1, and X2 is the point representation lying in S2. And S1 orthonormal is the orthonormal subbase of S1, and P1 is the orthonormal basis spanning S1, and the P1 orthonormal is the basis spanning S1 orthonormal. And we also define the coherence of representations of a subspace. Then the insight is if we maximizing the coherence of the subspace also belong to the benign one. And the weighted, and we maximize the coherence between this subspace and the weighted samples, like x times a. Then we'll have the following result, that the weights correspond to different class will have different values, and typically A will be small for the representation in X1, because the representation in X1 make no contributions to increase the output value, because they are orthogonal. And then the weight for the representation in X2 will be larger than that of X1. This is the insight of our algorithm, but actually we just have the mixed data, including X1 and X2, and we have no information about labels. So we don't have the P1 that is valid as well. So we have to estimate P1. And to make P, and we're replacing P1 with P, and P should satisfy that it should be closer to P1 than P2. Then we formulate.
So again, the attack, you know in which direction it is. So the attack is in P1. Am I right in that?
Okay. So,
P1 orthogonal basis spanning S1. Orthonormal basis spanning S1.
It's a plain blind data.
Right. So you want to get things in S2 or think in S1 close to things in S2 in a sense, right? Figure subs. Yeah, S1 is the good guy. Okay, S1 is the good guy. S2 is the greatest.
He wants to minimize the effect on X1.
Yeah, but are you thinking about the distance between the data in S1 and the data in S2?
I think the idea is to try and find a weighted combination of vectors in P1 and P2 that maximize what he's calling coherence. It's basically the cluster as much as possible is another way to think of it. We're trying to discover if there are two different classes of data. So we don't know. That's the idea. So we're trying to find this vector for the solution. It would be the vector A, and then we'll study the vector A to see if we can conclude that we have two different kinds of data or one kind of data. So that's the idea.
Okay. But a priori you don't know then what is S1, what is S2.
Yeah, we don't know.
Yeah, we don't.
Oh, you want to see if there exists.
Yeah. By studying the vector A that falls out of this, that falls out as a solution to this problem.
Oh, so in a sense, if all your good data is in S2, and then you start seeing some data in S1, so you see two kinds of data, you are able really to identify that you have two kinds of data.
Yeah.
Then you start asking questions.
Right. So if elements of the vector A are bimodal, if I see so if I plot them, distribution of A, and I get two modes, then the conclusion is, well, these must have come from two different, these correspond to two very different things.
Yeah, but like in general, if I think about pictures of dogs, I mean, you can have big dogs and small, like different colors or so.
Yeah.
So it's not always obvious that your data will always be the same.
Right. So that's where the first observation comes in, and that is that with messy data, the assumption is that it's not linear, but the neural network, what it does is as you go from layer to layer, it sort of unfurls it into, in the end, what the last layer is doing. Everything there lives in some sort of a linear space. So that's kind of the picture that this is based on. It's this idea that neural networks, as you go from one layer to another, it takes your data and it unfurls, it unwraps it. And then the last layer, you're basically just doing something like support vector machines or something like that.
Yeah, so just by looking at your last data, you don't want to see that half of the data is in one subspace, the other half is in a different subspace.
Exactly.
So, we didn't know the information, or we didn't know the labels. We just have the mixture data, and so in this case, we have to replacing P1, which is the subspace of the benign data, by P. P should be estimated, and it should satisfy the staying closer to P1 than P2. So in this case, if we solve this generalized eigenvalue decomposition problem, we can obtain optimize a weight, and it has some properties. The first is those weights on benign data should be smaller than that on on the point data, and this is motivate our detection method that A would be bimodal if the representations are point, and it should be unimodal if the representations are not contaminated. This is some examples for the first left figure.
Okay, can you go back, like again, the math question is you're maximizing over A, right?
Yeah.
And P is what?
P is like.
How are you choosing the
P?
P? Because you're saying, okay, P is close to P1 or closer to P1 than P2. Okay, that's
yeah, any P close to P1 than P2. And in practice, we just use SVD to conduct SVD on the whole data. So since the amount of whole data is very small compared to the benign data, so the conduct SVD on the mixture data, we can obtain like some projection directions that is very close to the benign data and far away from the point data. So, but we also have any other, there are many other ways to estimate P, but we use this very basic one, and we verify that in our experimental results that this P works better. Not better. It has a good functionality.
Let me ask you. Can I ask a question?
Okay.
So do you hear me?
Yeah, I can hear you.
So what is the interpretation of this the middle matrix I minus PP transpose? So basically, you are weighting each x with the square root of that matrix. So what does this represent? What does this matrix represent? Is it a kind of dispersion matrix or?
This you mean I minus P times P transportation?
Yes.
Transport. This is I go back to the slide. This is if P is P1, it spans the orthonormal subspace of S1. So.
Yeah, no, I understand the math, but what is the interpretation of this matrix? Why do you want to look at this? You want to maximize this functional precisely. So is it some kind? So do you penalize something? I mean, if P transpose is close to 1, or okay, no, never mind. Just go ahead. Thank you. It's okay.
Okay, thank you. So idea is if we if we assign each sample a weight and we maximizing the weighted sample, maximizing the coherence of the weighted sample and the subspace spanned by I minus P1 times P1 transport, we will get optimized A. Has some properties that the weight on the benign sample, benign representation would be smaller than that on the pointed representations, because the benign representations lie in S1, which is also normal to this subspace. So it makes no contributions to increase the coherence. So by solving this problem, it will assign the smaller weight on X1 and assign a larger weight on X2. So this is the insight. And we, based on this property, we can conduct a detection algorithm that A would be bimodal if because there are gap between A and which is more and which is another. So we can say that A would be bimodal if the representations are contaminated, and it would be unimodal if the representations are not contaminated. Some figure examples. In the left figure, this is the poisoned data mixture with benign data. So it approximately follows two model, a bimodal distribution, and the right figure is clean data without contamination. So it almost follows a unimodal distribution. And then the second property of A is that we found that A has a grouping effect, which means the absolute difference between any elements of A is smaller than a very small value. This means the highly correlated representation can be grouped into the same cluster. This motivates the backdoor identification algorithm. Just in this work, we just use a very simple clustering algorithm like k-means to identify the two classes, the poison classes. Yes, the poison class and the benign class. And the bottom two figures shows the grouping effect of the weight A, and you can see if A is contaminated, there are two groups, and if it's clean, it's almost one group. And then we show we conduct experiments on the traffic sign data. We use three attack schemes like a hidden trigger and TSAT and the badnet, which is the standard attack algorithm. First, we evaluate that this. In fact, this is a backdoor model has very high accuracy on the benign data, and the attack success rate is very high for those three attack schemes, which means the attack is successful. Then we record some results about the detection performance. We record the choose positive rate, which means it is the benign data, and it is sorry, this is detection. Yes, it is clean benign data without contamination, and we detected it as a clean data without contamination. And the false positive rate is that it is mixed data that is being contaminated, and we report it as clean data. So we can see that the true positive rate is very high and the false positive rate is relatively low. That shows that effectiveness of our detection method based on analyzing the weight state. And then we further conduct the identification result experiment by using k-means to identify the poisoned representation and the benign representation from the mixture one. We can see also we have very high true positive rate and relative small false positive rate. It shows we can correctly identify the poison sample and the benign sample from the mixture samples. And that's it. This is my presentation. Any questions?
So I'm again back to that. What's the terminology backdoor versus adversarial attack or stability, or so here it's because it's really a targeted kind of attack.
It's a targeted type of attack that you invoke, that an attacker can invoke at any time. So if they're not invoking it, the system works well. So you have a trained neural network that will classify things correctly until an attacker does something sneaky, and then it'll classify things wrong, like put a post-it note. So it's.
So this is not at the level of the training. Is it at the level of training or at the level of?
It is. It's done during training because it's the samples that you feed the network.
Oh, the sample that you feed. So
you inject poison.
Yeah, you inject something in the sample, but you can also inject something wrong in the image that is being classified.
Right. So
it can be both.
It can be both. So adversarial is just generally attacking the input, for example. But this is attacking the input in a very special way, where you've trained the network to misclassify it in a special way as well.
Yeah. So it's. So you want to find ways of saying, oh, there is something. There is a backdoor attack. Some of the data is really completely wrong.
Right. So,
versus the other kind of stability is really, you are thinking that you are preserving all your data.
Yeah, or you want, you're playing around with the input, I guess, with the regular adversarial attack. You just want it to give you bad output somehow. So it could be a good model, a clean model that gives you bad output.
Yeah. Okay.
So the message.
Is there any room for one question?
Okay. Yes.
Yes. Can you go back to slide 3?
Okay, I will share my screen.
Sorry. So the term in blue, lambda 2 times dx prime. Dx prime is 1 if x prime can be detected. So why do you want to minimize dx prime? I thought that you would minimize 1 minus dx prime, right?
I think it should minimize dx, not 1 minus dx.
If x prime is the poisoned sample, then you want to minimize, right?
Yes.
Very good.
Poison sample is If it is can be detected, the DX output 1. So if for many samples, many point samples should minimize the number of that can be detected. So I think it should be minimized. The X prime, not 1 minus D max, the X prime.
Okay, okay. So what's the relationship between this performance functional and the one you showed in later slides? Is there any intuitive relationship between
No,
these
it's
two?
just attacking strategy optimization problem for attacking, but what I do is on the defense side. They don't have any direct relationships.
Thanks a
What
lot.
You're saying is that this is how an attack is done.
Yeah.
But you don't know the specifics when you're trying to defend. So you get a model, a neural network, and you don't know if it's been backdoored or not. You want to figure out if it has. That's the right.
Sorry. Okay.
So you have a model,
Yeah.
and you don't know if it's been backdoored or not. And what you're trying to do is in the end say this model has been backdoored, or this neural network has been backdoored. Yes or no. That's the kind of what you're trying to do in the end.
Actually, it's like, I mean, it's very hard to distinguish between an attack or maybe the performance of your neural network is not good enough, right? I mean, you might get a misclassification, but not because of an attack, just because the performance was not good enough, right?
Yeah, right. But
okay.
So we target for that well-trained neural networks.
So you could distinguish between these two scenarios. You can say it was not an attack, it was maybe a misclassification because of the performance.
I don't think so. I think, I mean, if you look at the distribution that you showed one that's bimodal. I mean, then how bimodal is it? I mean, there, of course, the extreme cases are easy to distinguish.
But right in the middle is pretty
right in the middle. I mean, is this bimodal or is this just?
Right.
No, I don't think it's it's that kind that bulletproof.
A couple of questions. Like, the fact that your malicious data and your benign data live in two subspace, is it an assumption that are subspace or can be also subspace in general?
Sorry, a subspace or what?
Like the fact that there are the set of the malicious data and the set of the benign data are not just set but subspace. So they are linear subspace. Is this an assumption or is it something that you know that?
It's not. It's based on our experiments by analyzing the representations at each layer from the neural networks. We analyze the representations in each layer, and we found that at the last layer, because the data are separated and flattened. So based on this, we assume that the point representation and the benign representation, they lie in approximately lie in two linear subspaces, because at the next layer, they are almost linearized. It's based on some experimental results, not just only assumptions.
Okay. Then the second question, more curiosity, when you mentioned the attack goals, efficacy, fidelity, and the last the name specificity, exactly. And then you draw the three names on a triangle. Does it mean that?
Yeah, this should be a trade-off.
Like, if an attacker wants to prepare an act, cannot achieve all the three goals at the same time?
Yeah, there should be trade-off between these three goals.
That can choose only two of them.
Sorry?
Like, is that the fact that they are on a triangle, does it mean that an attacker can only achieve two of the three goals and not the third? Or is it just a picture?
They cannot only consider one goal, but yes, I mean, for the optimization problem, there should be some trade-off between different items. So the attacker should choose optimal one, like a trigger pattern and model parameter to like it have very high efficacy and and moderate fidelity, like that. But they cannot achieve all of the goals at the same time.
I guess the triangle is an arbitrary
Okay.
choice.
Because you synchronize these with the lambda values, right? You can put 0, 0, and then you focus on one objective, and you're like multi-objective optimization.
Right, yeah, so do the objectives work against each other? And the answer is yes. How much? Should we move on to our next? Thank you, Wenqing.